Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, we are going to discuss about the previous GATE question. This is the question on efficiency, the to maximum efficiency. Let's see, a 500 kVA three-phase transformer has iron losses of 300 watts, and full load copper losses of 600 watts. The percentage load at which the transformer expected to have the maximum efficiency is. The transformer at which condition it gets the maximum efficiency. The percentage load at which the transformer expected to have maximum efficiency is. That is, we know the formula. At what load we can get the maximum efficiency? X is equals to square root of iron losses by copper losses, square root of 300 out of 600, nothing but 1 by root 2. 1 by root 2 nothing but 0.707, nothing but the X value 70.7%. At 70.7% of load, we can get the maximum efficiency. This is the formula we used many times. Remember, this is very important formula. Are you okay? Let's see. A 50 kVA 3300 by 230 volts single phase transformer is connected as a auto transformer shown in figure. The normal rating of the transformer is. So we have to find out rating of auto transformer. Let's see. This is my auto transformer they given. See, for example, current direction is like this. Here the current leaving, and here also leaving, nothing but both are leaving, nothing but additive polarity. That's why 3300 plus 230 is equals to 3530 they given already. So now tell me, the kVA rating of auto transformer is equals to 1 by 1 minus k times of kVA rating of two winding transformer, where K is equals to LV by HV. LV is the 3300 and HV is the 3530. 0 gets cancelled. Now let's K value this much. So substitute here 1 by 1 minus 330 of 353 into the kVA rating of two winding transformer 50. So 353 out of 23 of 50. This is the value. We have to solve it. this. So if you solve this one, you can get the answer of 767.4 kVA. 767.4 kVA. This is your correct answer. Or directly you can say, I said you already, what is that? For 3300 by 230 volts, the rating is 50. For 3300 by 3530 volts, how much? These are common factors. So 3530 into 50 by 230 is same. So the answer is same. 767.4 kVA is the rating of my auto transformer. This is the shortcut I said you, and this is the formula. and by the analysis also you can get the answer, but that is lengthy. This formula or shortcut, anyone you can use, you can get the answer within fraction of seconds. Right? Got it? See this problem in this video. A resistance and reactance of a 100 kVA 11,000 by 400 volts delta star distribution transformer is 0.02 and 0.07 per unit respectively. The phase impedance of the transformer referred to the primary is, they want to, the phase impedance referred to the primary. Generally we know that the impedance of delta is equals to 3 times of the impedance of the star. You should remember this first of all. And next one, see here, we know the per unit impedance they given 0.02 plus 0.07. This is the per unit impedance of primary as well as per unit impedance of secondary. For both this is same, because all per unit values are same for primary and secondary. This is okay. Next they want Z actual value of primary. Z actual value of primary. So I said you already, Z actual value is equals to Z per unit into Z base. Here Z per unit into Z base, Z per unit we know that 0.02 plus 0.07, but Z base we have to calculate. Generally, Z base is equals to formula V by I. Of course we know, but we know V but we don't know I. How we can calculate? V by kVA by V. kVA by V is the current. So finally Z base is equals to V base by kVA base. V base by kVA base. Now substitute in the Z base. Z base is equal to V base primary. Primary V base nothing but 11,000 square by kVA base. kVA base is the this much. But this is not enough. This is not exactly correct answer, because I said you in delta the impedance is more than star. So we have to take here 3. This is the answer. The Z primary in terms of ohms is equals to, if you calculate this value, you can get 72.6 plus J 254.1 ohms. This is the impedance referred to primary. Here this 3 is very important. We have to multiply with 3. Then only we can get the answer. This is the impedance, per unit values and actual values. I said you already, Z per unit is equals to Z actual by Z base, where Z actual is equals to Z per unit into Z base. Like that we have to calculate the answer. And Z per unit values are same for primary and secondary. Z base values are, we can find out. This is the problem on impedance, per unit and actual values. Understood? On load sharing in parallel operation, 2 transformers are to be operated in parallel such that they share load in proportion to their kVA. They share load in proportion to their kVA. The rating of the first transformer is 500 kVA and its per unit leakage impedance is 0.05 per unit. If the rating of the second transformer is 250 kVA, its per unit leakage impedance is very simple, direct statement. We know that generally in parallel operation, the load sharing is directly proportional to per unit impedance. And they said that such that they share the load in proportion to their kVA rating. They share the load, the load is proportion to their kVA rating. At this condition, when the load is sharing proportion to their kVA rating, at this condition, the per unit impedances should be same. The per unit impedances should be same. When the transformers share the load proportion to their kVA rating, at that condition, the per unit leakage impedances of two transformers should be same. Then only, when the per unit impedances are same, then only they share the load proportion to their kVA rating. So what is the answer? So the answer is again 0.05 per unit for second transformers also, because they share the load according to their kVA rating. This is the direct statement in parallel operation. Are you okay? Understood? Right. This is a linked answer question. Common data is there and they will ask you two questions, linked questions. If you get answer here, then you can get answer here also. If answer is wrong here also you can get wrong answer. So be careful. Linked questions, very important. Generally nowadays there is no linked questions in GATE exams, but this is the previous GATE questions. Even though we are going to solve this easily. So see here, a 300 kVA transformer has 95% of efficiency at full load, 98% of efficiency at full load, 0.8 power factor lagging, and 96% at off load unity power factor. 95% at full load, 0.8 lagging, 96% at off load unity power factor. They given the data. Now the question, the iron losses in kilowatts under full load operation. They asked that the losses, see here options, copper losses, iron losses, copper losses, iron losses. They want the copper losses and iron losses at full load operation. At full load operation they want that. Not in off load. Full load operation they want. So let's calculate. First, efficiency is 95%. 95% of efficiency is equals to full load. That's why kVA into power factor by kVA into power factor plus iron losses plus copper losses. We don't know iron losses, we don't know copper losses. So if you solve this, you can get the iron losses plus copper losses value by solving this. You can get the iron losses and copper losses value 12631.57 watts. How much? 12631.57 watts. This is the combined iron losses plus copper losses. But not completed. Separately, we want separately copper losses and iron losses. But you said that combinedly iron loss and copper losses. Let's go for next data. And 96% at offload unity power factor. Let's draw the here 96% at offload. So half of the 300 kVA and unity power factor. Half of the 300 kVA unity power factor. Iron losses same, but copper losses are offload. That's why by 4th. Like this. Now simplify this and you get iron losses plus copper losses by 4 is equals to. Simplify this. You can get the answer of 6250 watts. 6250 watts. This is at full load and this is at off load, and the iron and copper losses, two equations we got. by solving these two equations. If you solve these two equations, then you can get the copper losses of 4122 watts and iron losses of 8508 watts, like this. You got these values, copper losses and iron losses. You got these values, these two values, approximately these two values. From this, tell me 4 point, yeah, they asked in terms of kilowatts. 4.1, okay, it is right answer. 8.51, of course, this is also right answer. So option A is correct answer at full load losses. Option A is correct answer at option A is correct answer for given. What is that? What is that? Copper losses are 4,000. Copper losses are, oh, here two options are there. Here two options are there. Be careful. Be careful. Same two options are there. So if you solve this, you get iron losses of 4,000. Iron losses are less than copper losses, right? So iron losses are this much and copper losses are this much. Now tell me, which of the following is correct answer? Always iron losses less actually at full load. So option C is correct answer. Iron losses are 4122 watts and copper losses are 8500 and change. So finally the answer is this one. The answer is this one, option C. Iron losses 4000 change and copper losses 8000 change. This is the first question. This is the first question. Next, what about second question? What is the maximum efficiency at full load? What is the maximum efficiency at full load? First of all, to know the maximum efficiency, we have to know the X value. At what load we can get the maximum efficiency? X is equals to iron losses. Iron losses are 4122 by copper losses are 8508. If you solve this, you can get an answer 0.696. Nothing but at 69.6% of load, we can get the maximum efficiency. So calculate that maximum efficiency. That maximum efficiency is equals to 69.9% of 300 into unity power factor by 69.6% of 300 into unity power factor plus, what is that? Iron losses. What are the iron losses? 4122 plus copper losses. But remember, to get the maximum efficiency, copper losses is equals to iron losses. Copper losses is equals to iron losses. So this is the maximum efficiency. If you solve this, you can get the answer. If you solve this, you can get the answer. Which is correct answer? Solve it and see which of the following is correct answer. You have to do this answer. I won't tell you, okay? So solve them, and go for which of the following is correct answer. This is the procedure, how we have to do the problem just. First of all, they given at full load and off load. So at full load, one equation is there, and at off load, one equation is there. If you solve these two equations, then you can get iron losses and copper losses. Then after, I want maximum efficiency. So I have to know at what load we can get the maximum efficiency. So I got some load. At that load, we have to find out the efficiency. That is my maximum efficiency. That maximum efficiency, I given you numericals. Just solve it. Don't see simply. Just solve it and give the which of the following is correct answer. Can you tell me anyone? Can you tell me anyone? Which of the following is correct answer? Yeah. Option B, 96.2% is the correct answer. 96.2% is the correct answer. Right? Okay. This is a linked answer question. If this answer is wrong, then automatically this answer also wrong. So be careful in linked answers. First, if this is right, then only the second one also is right. Right? In this video, the question on auto transformer, let's see a single phase 50 kVA, single phase 50 kVA, 250 by 500 volts, two winding transformer has an efficiency of 95%. The two winding transformer efficiency given. At unity power factor, full load unity power factor efficiency given. If it is reconfigured as a 500 by 750 volts auto transformer, 500 by 750 volts auto transformer, its efficiency at new rating, its efficiency at new rated load and unity power factor will be. Now we want efficiency of auto transformer at new rating. First of all, they given efficiency of two winding transformer 95%. 95% efficiency at full load. So full load, that's why kVA 50 and power factor unity by 50 and losses. We don't know the losses. Losses won't change. Only kVA rating change from two winding transformer to auto transformer. So now find the losses. Now find the losses. So what is the losses? If you calculate from this, you can get losses of my two winding transformer is 2631.5 watts. If you calculate from this, you can get answer 2631.5 watts of losses of two winding transformer. The losses are same for auto transformer exactly. Next, if it is reconfigured as 500 by 750 volts, what is that? 500 by 750 volts, nothing but what is K here? K is equals to LV by HV, nothing but 2 by 3. kVA rating of auto transformer is equals to 1 by 1 minus K times of kVA rating of two winding transformer, 3 by 2 minus 1, nothing but 150 kVA is the kVA rating of auto transformer. I got kVA rating of auto transformer. Now I have to calculate efficiency at new rated load and unity power factor. So find the efficiency. Efficiency of auto transformer is equals to full load. So 150 kVA into power factor by 150 kVA into power factor plus losses. There is no change in losses. The losses are same 2631.5 because they won't given the details about losses. So efficiency, if you calculate this, you can get the efficiency 98.27%, 98.276%. If you calculate, you can get the efficiency 98.276% is our answer. This is generally the efficiency of auto transformer. Are you okay? Understood? Very simple. Just I find kVA rating and substitute it, then I can get the answer. That is the efficiency of auto transformer. Right? So see here, three single phase transformers are connected to form a three-phase transformer bank. To form a three-phase transformer bank, the transformers are connected in following manner. The transformer connection will be represented by. Let's see. Actually, this is a star delta connection. In star delta, we have a 4 configuration. One is 0 plus or minus 30 degrees. One is 180 plus or minus 30 degrees. Nothing but either plus 30 or minus 30 or 150 or 210. Nothing but plus 30, nothing but leading, nothing but 11 o'clock, 1 o'clock, 5 o'clock, 7 o'clock. These are the actually what are the possibilities of phase differences. But in star delta, there is no possibility of 6, there is no possibility of 0. This is must and should. First of all, these two removed. These two are the wrong answers. Now, 1 or 12. Let's see. First of all, draw the arbitrary star. Draw the arbitrary star. I am drawing the arbitrary star. This is the arbitrary star. A2, B2, and C2. This is the arbitrary star. Now corresponding arbitrary delta. These two are like a additive manner. These two are additive in manner. If there is no dot notations, we have to take here dot notation. These two are in additive manner. For additive manner, the vectors should be same. So let's see. This is A vector. The A vector is same. A vector is same. Okay. A vector is same. Next, B vector. The B vector also is same. B vector is also same. This is A, this is B, and this is C vector, and C vector is also same, and C vector is also same. C vector is also same. This is a C vector. A, and B, and B, A, B, and C, and C. A, B, and C. These are the three vectors. What they are? Arbitrary equal of this star. See here, first A is in between A2 and B2. A is in between A2 and B2. B is in between B2 and C2. And C is in between C2 and A2. C is in between C2 and A2. And take the dimensions. This is superimpose on a clock. Superimpose on a clock. 12 o'clock, 11 o'clock, 1 o'clock. Now see, this primary is the minute sign. Primary is the minute sign. And secondary is the hour sign. Secondary is the hour sign. My hour sign is here. My hour sign is here. Then tell me how we can represent this. Primary is the star. Secondary is the delta, and time is 1 o'clock. Primary is the star, secondary is delta, and time is 1 o'clock. So option B is 100% correct answer for given data. Option B is 100% correct answer for given data. This is very simple. We saw already star delta, delta delta, star star, delta star, star delta. All the configuration I given you already. Just go through them and be careful. Don't make a mistakes. Okay? Understood? The question on EMF basic principles. Let's see. The core of a two-winding transformer is subjected to a magnetic flux variation as indicated in the figure. This is the transformer. Primary having 100 number of turns, secondary having 200 number of turns, and this is the flux. The flux variation is given like this. The induced EMF in the secondary winding, as a function of time will be of the form. So how the induced EMF is there as a function of time. How the EMF will induce as like this. They are asking question. What is the EMF waveform? They want the EMF waveform which is induced in the secondary of my transformer. Let's see. Generally, we know that the formula E is equals to minus n into d phi by dt. E is equals to minus n into d phi by dt. This is the formula for EMF to produce. See here, this is the flux, and from first interval to second interval, there is no change of flux. Nothing but d phi is 0. If d phi is 0, there is no EMF produced from first segment to second segment. There is no EMF will produce here from first to second intervals, because there is no change. If DC supply given to a transformer, no EMF. Like that, this is DC, no EMF produced in these intervals. Next one, from 0 to 1, from 0 to 1, from 0 to 1, E is equals to minus n into, n is the 200, minus n into d phi by dt. Can you tell me what is the d phi? What is the change in flux? The change in flux is 0 to 0.12. Nothing but the change in flux is 0.12, and the change in time is 1 second, and the change in time is 1 second. This is our answer. So what is the answer? 0.12 into 200, nothing but minus 24 volts. Minus 24 volts. 2 12s are 24. So in this case, the voltage is minus 24 volts. Minus 24 volts. This is the minus 24 volts. Between the time interval 0 to 1. Between 1 to 2, there is no induced EMF. Next, between the time interval 2 to 2.5 seconds. 2 to 2.5 seconds. Between the time interval 2 to 2.5 seconds. In this period, E is equals to minus n into d phi by dt. What is the change in flux here? What is the change in flux here? The change in flux is from 0.12 to 0. So the change in flux is minus 0.12. Minus 0.12. Because the change is nothing but 0 minus 0.12. 0 minus 0.12 is the 0 minus 0.12 is nothing but minus 0.12. But here the change is 0.12 minus 0. 0.12 minus 0 is nothing but 0.12. Here, what is the time? What is the time? 0.5 seconds. 0.5 seconds. So, if you calculate this, minus into minus plus, and this is 24. 24 by 0.5. 24 by 0.5 is nothing but 48 volts. So, the EMF induced in between these intervals is 48 volts. 48 volts, and here is minus 24 volts. Minus 24 volts. This is the waveform of EMF which induced in the secondary winding of my transformer with this flux variation. Here, the only thing is that E is equal to minus n into d phi by dt, and there is no change of flux. There is a change from 0 to 0.12, nothing but 0.12 minus 0. Here 0.12 to 0, nothing but 0 minus 0.12. Then you can get the answer exactly. This is a very basic question but very important for competitive exams. Right? Did you understand? Okay? In this video, a special question on three-phase transformers. I said you one question also on this. So see here, common data they given. This is star delta connection. The star delta transformer shown above is excited on star side with balanced 4-wire 3-phase sinusoidal voltage supply. Balanced 3-phase 4-wire supply voltage of rated magnitude. The transformer is under no load condition. My transformer is under no load condition. Now my question is, with both S1 and S2 open, both S1 and S2 open, then the core flux waveform is, when S1 is open, there is no closed path for third harmonics in the primary, and there is no closed path for third harmonics in the secondary because S2 also open. There is no closed path for third harmonics in the primary and the secondary. Hence, at this condition, I mu is sinusoidal. At this condition, I mu is sinusoidal. At first condition, I mu is sinusoidal. If I mu is sinusoidal, then the core flux waveform is flat tapped. Core flux waveform is flat tapped. The core flux waveform is flat tapped. When I mu is sinusoidal, then the core flux waveform is flat tapped and EMF waveform is peaky wave. Remember this, I told you already, right? So at this condition, when both are open, I mu is sinusoidal, then the core flux waveform is flat tapped with harmonics. Flat tapped with harmonics. This is the first question answer. Next one, second question. S2 closed but S1 open. Here S2 is closed even though S1 is open. Then the current wave in delta. Actually, S1 is open and S2 is closed, and this transformer under no load condition, that's why there is no currents actually, but due to closed delta, the third harmonic currents flows in the delta. It provides a path for third harmonic currents. That's why sine at fundamental frequency wrong, flat tapped is the wrong, only third harmonic components flows in the delta. Only third harmonic currents flows in the delta because this is open and this is closed and there is no load condition. Only the harmonic currents, third harmonic current circulates here. That is only third harmonics flows in the winding. This is very simple question. I explained you in concepts also. Very simple question. This is also very important for competitive exams. Listen carefully. Listen once again. When this is open, there is no closed path for third harmonics. When both are open, there is no closed path for third harmonics. Hence, the I mu is sinusoidal and the flux is flat tapped. But when S2 is closed, S1 open, and there is no load condition, hence there is no load currents, but due to closed one, it provides a closed path for third harmonics, hence only third harmonic currents flows in the delta. This is simply the question, very important. Understood? Thank you, sir.